So today we are talking about STM. Uh, okay, apparently Dylan is rating us because there's some people calling for CH road and so on and so forth. So welcome everyone. If
Welcome,
folks are
everyone.
here, as I was mentioning, today the topic of discussion is a little bit of a sideline from our usual topic. Again, just to contextualize a little bit why we are even doing that, um, in the recent weeks, we've been hacking a lot on effect cluster together with Maxwell. And last time, um, we've while on streaming, I was kind of made aware of some state management troubles, or to put it better, there are some cases where we might end up with inconsistent states and so on and so forth. And I thought STM was a great choice to resolve those types of issues. But given that effect is so wide, even core contributors such as Maxwell and myself, there's not a single person who knows uh, all the modules of the effect ecosystem, and I'm lucky enough to be the one that worked on STM and core, so that's sort of my domain. And Maxwell, while he has worked a lot on core, he has never had the opportunity to touch STM. So I was like, that it might be fun to actually do a little bit of a sideline and for once stream about STM while you're learning the new module. So I guess we can start with me screen sharing a little bit and just explaining the very basics of STM. Why is it even relevant for the use case, and just making a few examples of how it works, and then we can take it from there wherever we want. We can hop on your screen share or just close the call, trash STM. Uh, we can we can decide at a later point what to do. So let me figure how to screen share from here. Okay, there's a screen share button. That's probably where
Sorry,
this
Dylan,
should start from.
you're not getting your wish, at least not till later.
What's Dylan's wish?
He said, hopefully Max is driving so we don't have to look at BS comments.
Just use a real editor. Okay. Do you see my screen? Yes, you
Yes.
should. So STM play.ts. Font. Is it fine?
Yeah, I think
Should
maybe you
I?
could zoom in just a tiny bit, but I think overall it's pretty good. Yeah, that's good. If any of the people watching can't see the text or anything like that, let us know.
Or, mind your business. But that was indeed a joke. Anyway, let me make this full screen. Good. Like a great idea, I have an embedded terminal. You see, Dylan? I can do pnpm tsx scratchpad stm play, and it's gonna say nothing because we haven't done anything. So let's start by importing a module which is called, again, STM. First of all, we should say what STM stands for. Uh, it's not an invention of effect, but it's a widely used technology in other languages. It's called software transactional memory. What it means, if you are familiar with things like database transactions, it's kind of doing the same with regards of data structures within the language. So instead of having transactions in a database, you would have transactions, for example, between a transactional map, a transactional reference, and so on and so forth. This is very important in cases where, for example, you have parallelism to avoid race conditions. Uh, that's not the case in JavaScript, though. Given JavaScript is single-threaded, one might even ask why is it even relevant? Well, anytime we have anything asynchronous, there may be race conditions. Even though nothing happens in parallel, there can be asynchronous race conditions. And STM is a way of avoiding those. Now, the how it works, I will start by doing a very simple example. So first of all, STM is exposed as a module. Just if you're familiar with Effect, it's roughly the same type of API, but there are two fundamental differences. Well, three fundamental differences. The first, it's fully synchronous, so you can't embed anything asynchronous in it. You should also avoid embedding any side effect on it because of a point that I'll make later. So that's the first fundamental difference. The second fundamental difference is there's no concurrency primitives whatsoever. And the third fundamental difference is that an STM computation may happen multiple times. So it may be retried. And now I'm going to get to the point. Basically, an STM transaction is retried up until the point where it can commit, either successfully or by failing. Which means that anything you write within STM must support being able to run multiple times. Which means, for example, if you have a console log, you might have the console log triggered multiple times instead of just one. So let's begin by writing with our very familiar type of API. If you're coming from Effect, let's actually start with Effect in the first place, and let's do something different. Let's start with Effect, and first of all, I want to create a transactional ref. Transactional refs are just like references for Effect purposes. The API of a tref is very similar to the API of a ref. The difference is that it can participate within an STM transaction. So STM is a subtype of Effect, so you can just yield an STM computation. Behind the scenes, what this is doing is stm.commit with the actual STM transaction. And when we commit the transaction, you see that we get back an effect, a normal and plain effect. Let's remove this commit, given it is not strictly necessary. So now we have our tref. As I mentioned, we can do the same type of operations that we do with a normal ref. So, for example, we can increment it. Given it's a number, we're updating the value of the ref. But differently from a normal reference, what we're doing now is something that is unique to STM. Let's say that we have a computation, so some effects that in order to run, we need to wait for the reference to be 10. So instead of just updating once, we're going to update multiple times, the counter starts from 0. The moment we hit 10, we want an effect to start. How would we do it? Well, we would make an STM transaction, which is called wait for ref to be 10. Now, of course, naming, you wouldn't name it this way, but given I'm good with naming,
this is how I write
it's
my code. So
well, let's say we do then an STM gen function, and in here we say the current value. We do tref.get, and we get the ref. We then check, is the current value 10? Now, current value is hopefully a number. Yes, it is. If it's that, then we're done. We can return. Otherwise, we return yield stm.retry. This is the core primitive that allows STM to wait on arbitrary conditions between transactional values. So what we're doing here, and of course we could just make this a little bit better. Maybe this is slightly easier. So this returns an STM value, which again is an effect, so we can run it normally in effect. But this will retry up until the point where the ref is 0. Now, one might ask, is it performant enough? Because if we do this in a loop, if we were to do this with a normal ref and just write a loop that waits for this to be 10, the loop would consume all the CPU resources. So that's not what is happening in this case. The STM retry waits for any accessed state to change before trying again, which means that when we update the reference, we are actually updating a shared journal, and this will retry anytime we update the ref. Will not just loop casually, and we can see that happening in a moment. So let's say that we have a process that we wanna effect.repeat. Actually, we wanna do that forever. We might wanna add a small delay, just 100 millis delay after every increment, and we're gonna fork scoped this thing. So this is when this program runs, we're kicking off a fiber that ends up updating the reference every 100 millisecond. And now we want to kick off a different fiber that first does the wait and then does flat map effect.log info. Now the ref is at least 10. To be precise, this should retry while the ref is less than 10. No, actually, that's fine. It should retry. It can retry anytime it's not 10 because it's gonna start from 0 and it's gonna retry at any point in time. So let's see what this program does. I need to also fork scoped this, and actually no, I don't need to fork scope this. Mm, let's say that this is our main program, and we need for it to be scoped. Actually, I can just fork here, and then we don't need the scope, just to make things a bit easier, and say that we run to a promise. Let's try to run this, and it's printing whenever this hits 10. So this waiting actually works. But let's check, given I've said these retries, retrying. We make a counter. Just to check how many times are we retrying. Hopefully we are not retrying more than 10 times. There we go. So this is the very, very, very level 0 introduction to STM, which I call it a primitive for coordination. Might be easier to understand in terms of coordination versus transactionality. Now I'll stop for a minute. Maxwell, please, if you have any question up to this point, please fire them off.
So far, I am tracking. I'm just answering like some
Okay.
questions in the chat, but I'm tracking you so far.
Any interesting question that we should highlight?
No, there was a question about why we needed scope, and I was typing the answer, but I guess I can just answer. The scope was originally required when Mike was forking the fiber lifetime into a scope. So when using fork scoped, you fork a fiber and you attach the lifetime of that fiber to the scope. But in this particular case, there was really no need to do that. So we just simplified and used fork. So we did not need the scope.
And the reason why we don't need the scope now is the program ends here. So the fiber that was forked to run this program ends. And when that fiber ends, all of its children also end. So this fiber that we fork here is automatically stopped when the program ends.
Yeah, fork scoped is useful to attach fiber lifetimes to scopes so that like if the scope is closed for some reason, that the fibers attached to that scope are properly like interrupted, and that it can be useful, especially like when you're forking background processes into like a layer that you're attaching to your program or something like that. But for this particular case, we didn't need it. We used the
And
automatic supervision.
just to show the differences, if I do a fork daemon, this program will not end. You see, this keeps going. This keeps going because there is one fiber running, so I have to kill it manually. And fork scoped instead attaches that lifetime to the scope, and here I could, for example, do pipe effect dot flat map effect dot log info saying program ended, and after that doing effect dot scoped, and now the fiber will be killed off after the program ended, because we are closing the scope. So that fiber will now outlive the life of program. So when program is finished, that fiber will keep running, but once the scope is closed, that fiber is also closed. So it's a way to manually control the lifetime of such forked fiber.
And just
But again, to simplify, we don't need that here.
to add one clarification to those who might not be familiar with like all these fork APIs, fork, like Mike said, uses auto supervision, so it attaches the lifetime of that child fiber to the parent that's forking it. Fork scoped, like Mike said, attaches the lifetime of the fiber to a scope, so that when the scope is closed, the fiber is like be able to be
Also
interrupted.
closed.
Yeah. And then the fork daemon or fork daemon, however you pronounce it, attaches the lifetime of the fiber that you're forking to the global scope of the program, which is why when Mike used fork daemon, the program never ended because we were using effect.forever. So that fiber just kept the process open. So all of the fork APIs are just ways to control fiber lifetimes in like more granular ways and can be really useful for different scenarios. Anyways, not to derail our STM discussion, but that was a good opportunity to talk about forking and its behavior.
No worries. That's always helpful. But again, as I was saying, this is kind of the very basic of STM. Mm, I could have two references and update it in two places. There are two current one, current two, have two, current one. And this hopefully works the same, with the exception that it is retried a few times more, because here we are accessing two different references and we are changing the value of the two references independently. We have about 20, um, exactly 20, 20 updates before our condition is met. This is called an STM transaction, and this is an effectful program that waits on an STM transaction to occur. So this would be like your, if you were to write this in database terms, you would commit such transaction. When this transaction is committed, it's properly returning. Now, there are some databases that works exactly in this way, and those are databases that leverage optimistic concurrency. So they start doing all the changes. If then they have a conflict, they retry up until the point this works. So you can mix any amount of things in any amount of transactional data structures in an STM transaction. Let's say that, for example, I want a T map. And we're starting the T map. Actually, we're doing an empty map string to number, and our map, we do an STM. Actually, let me think about something. I want to add new entries to the map dynamically. So we do that forever. What can I do? So let me generate a random number. And let's add tmap dot set. So here we are setting values every 100 millisecond, and our condition could be that the tmap size of a map and running this should reach the condition. I think we do want to re-add our console log retrying plus and equal 0.
It looked like the tmap structure has a couple of like interesting methods on it, like setting only if something's like absent and stuff like that as well. I mean, those are, I guess, reasonably basic operations, but could be like interesting to be able to mix different logic, like retain if, remove if. Those are like some interesting operations that you have access to with a tmap. It's kind of interesting.
Generally speaking, a tmap, we can create our own tmap to an extent.
Yeah.
Let's try to do that just for the sake of argument. Let's have a hash map and let's have a tref. Our tmap will be a tref of a hash map. What was it? String number. So we have a reference, a transactional reference to an immutable map. Our set would be our tref.update. We would update our map and we would get our hash map here. Hash map dot set. It's pretty much exactly the same code
Yeah.
as before. Now we do tref.get on our map, and on it we do a hash map.size, and this ideally would work exactly the same.
It's probably not too dissimilar from how tmap's implemented under the hood, if I had to guess.
I
I mean, I don't remember.
wouldn't. I don't remember that. We can check.
Yeah, might as
For the
well.
sake of it, we can actually check. Tmap, 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 tmap.
A
No,
team. It's got buckets and a size and a not at all.
not even close.
But it does look like
But
it's basically got a chunk of what was the buckets? It was like a chunk of references or something like that. Chunk of no,
no,
transactional array of
it's
chunks
a
of
reference to a transactional array of chunks. It's beyond me why it is implemented in this way. The reason is it was like that in Zio, but most likely is due to performance to an extent. and maybe the ability of some of those operations may not be uh, implementable with a hash map, even though I'm not that sure, because I think I could implement all of them on top of a hash map. Unsure. Again, I was porting from Zio, so at some point we might actually want to reevaluate some of those structures.
Yeah.
But now to the interesting point: how many structures do we actually have that are transactional? So there's a T array, there's a T deferred, there's a transactional array, transactional deferred. We have a transactional map. We have a transactional priority queue, transactional pub/sub, transactional queue, transactional random number generation, reentrant locks, references, semaphores, sets. And for the time being, those are the structures we have, but we could add more. For example, we have a tree utility, we could have transactional tree. Uh, the difference is usually mm, you lose a little bit of performance, because if we think about, for example, what happens here, we are updating a reference with a hash map inside. So there's two operations instead of one, and the whole thing may repeat multiple times. Now, not this specific case, because this is doing a single change, but transactional structures are usually slightly less performant than non-transactional structures. For example, we have a semaphore in effect, so effect.make semaphore, which is extremely optimized. And then we have this T semaphore, and if I show the implementation of the T semaphore, it's just beyond simple. Well, that's the only thing. Basically, it's a T-ref of permits. Acquiring the semaphore takes a permit, releasing the semaphore does +1 on the permits. Period. And everything else, you have it. How would an API like with permits 1, with permits 2 work? You would have an acquire release, acquire use release, so effect.acquire use release. Actually, I think we can even see that with permit, with permits. Okay, slightly more contrived, but we're basically acquiring end permits, then running the effect, and ensuring that after the effect is run, we release the permits. And again, if I show the release end, it's using a lower level API for performance, but you can pretty much see that basically what is happening is it does +1, the plus n on the thing. Uh, Here it uses basically the directly the journaling to avoid doing too many reads. So some of those are implemented in slightly lower level terms for performance reasons, but it could just be implemented as a T-ref of permits. And the beautiful thing is that you could mix them up with different things. So, for example, let's say that I have two different semaphores, and for a specific effect, I want to acquire both for it to run. Now we are in a conundrum, because if I do it with the normal effect semaphore, it might deadlock. Why? Because let's say I have different operations. Some use the first semaphore, some use the second semaphore, and one uses both. If I acquire first the first semaphore, I'm blocking that. But if I have another process that is using the first semaphore, then that process also stops. The point is, there's no way of saying I need to acquire both semaphores or none of those. There's a way of saying I acquired the first, and once I have the first semaphore, I can acquire the second one. But there is no way of saying I want to acquire both. With STM, there would be a way of saying acquire both. I just need to take them both. So let's say, for example, I have an STM and I have a T semaphore. Let's actually do that just for the sake of saying it. Let's say const sem1. Let's say T semaphore dot make with a single permit. So here I have two separated T semaphores. Const with both semaphores. Score it with both. And in this case, I want to accept an effect. Again, the objective is for this to run if both semaphores can be acquired and released, of course. Say acquire use released. The acquisition stage, let me do an STM transaction. Let's say
There's a question in the chat about, is there any simple rule by which I can determine if I need to use STM?
I think it's a factor of pain to an extent. If you have synchronization problems between multiple things, STM might be the solution for it. For example, we're going to see an example later where we're working with queues. And we're going to start with the effect queue, the normal effect queue. And then I'm going to ask a question: how would you take an element from either the first queue, if there is an element, or the second queue, if there is an element? And we're going to discover that this problem is not solvable with effect queues. And even if we solve it, it would be extremely inefficient and unsafe under interruption. So with STM instead, that's going to be 2 lines of code. Anytime you need to synchronize multiple things, probably you need STM, which is rare, to be honest. Especially in app code, that's very rare. Which is why, for example, Maxwell never had the chance of trying out the module. Now, I think after knowing the details about the module, use cases may arise. There may be moments where you say, "Oh, I might have used STM for this specific thing," and you found a different solutions. But generally speaking, when you need synchronization and things waiting on specific conditions to kick off, that's the moment you need STM, or the moment you would benefit from writing the same with STM without too many dirty tricks that you would have to do otherwise. So in this case, I hope I have answered Or
Yeah, like I think another like point I might add is like for example, the development we're doing on effect cluster. Like what we're doing is theoretically possible with just effect primitives, but it's much more difficult to coordinate all of the things that I need to keep in sync. So it might make sense for something like, for example, the entity manager that we were discussing the last time we were talking about cluster. It might make sense for me to explore whether or not using STM to synchronize all of the different things I'm trying to keep track of. It might make sense for me to use STM for that. It might not. It's more about, like Mike said, like if your use case is that you need to synchronize multiple things that you're having trouble keeping in sync, and that they also might need to wait on certain conditions before you can run different effects and things like that. Um, STM might be a good solution, and it might not, but it might be like it's kind of like there's no like rule, so to speak. I think it's more of like another tool to keep in your tool belt and to pull it out when like you need to use it.
and especially in the cases where you need to use it, doing it without, albeit sometimes possible, is unbelievably extremely hard. Like if I show the implementation of the normal effect semaphore versus the STM semaphore, in STM it's 2 lines of code. In effect is 40, 50 different lines of code of very low level and very hard to maintain code. And debugging 2 lines of code is easy. Debugging 45, 50 lines of very low level code can be a nightmare. And given you are really testing against race conditions, even realizing if you have a problem is absolutely not easy. So I would say if you have synchronization issues, unless you have extremely good reasons not to use STM, using STM is a safe bet. At worst case, you're gonna remove it at the end for very similar APIs. So that's probably the rule. Well, let's keep going with this. So here I have an acquire use release. So the first is the acquisition state, the second is the use, and the third one is the release state. Say release, release. So that's how I would acquire 2 semaphores. And this effect will not run if it doesn't acquire both semaphores. But the difference with doing the same, like one might ask, this is the STM version. Let's program effect make semaphore, effect make semaphore. It's called take.
There's another question about in the STM implementation, should the semaphores be released in the opposite order? But I don't think that the order of release necessarily matters because the STM transaction's happening atomically.
You got it. Doesn't
Look,
matter at all.
look, we're learning. We're learning, chat.
Um,
I think in the first, in the acquire, you're taking 2 permits from the second semaphore.
yes, of course. So while optically those two things are the same, they are completely different. When this runs, First, it takes the first semaphore. Anybody else who tries to take the first semaphore will not succeed because the semaphore is taken. Then it takes the second one. So if the second one takes, um, a month to acquire, you're blocking the first one for a month. In this case, they're both taken at the same time. And the first one is not taken if the second one is not available.
It may be even
And
more
the reverse
illustrative.
is the same.
It may be even more illustrative to show the actual race condition here, where we like have an effect in our program effect. We can have like one program that immediately takes the first semaphore, and then our with both tries to run, and then we have a second effect take the second try to take the second. So we have three effects that are like essentially in a total deadlock in the.
Yeah, let's see how I can create a deadlock. How can I create a deadlock from here? Um,
So I guess the first thing we would need
so
is
first, I need to run something that takes the second semaphore.
and also just to be clear, while Mike is thinking through this for the chat, what we're doing here is very contrived on purpose so that we can show like in like very few lines of code what actually is going on with these semaphores. But in an application where you might have layers that contain semaphores that are being accessed by multiple different effects within different fibers, et cetera, like having guarantees when you're in situations like this is extremely important to avoid deadlocks. So what we're doing here obviously is contrived, but like in an app code, when you're managing this like situations like these, I'm already starting to see like the areas where STM could potentially like be beneficial, even in cluster, for like providing guarantees basically.
Now, if I want to generate a deadlock here, I'm gonna have to do something slightly dirty because it's a minimized example. But the point being, I would first have to run this that requires both. But as soon as the first one is taken, take the second one from somewhere else. And
So we can
then once that occurs, inside there,
we basically like
retake the first one.
yeah,
It's
we might be
it's
able
not. It
to
might be a little bit too contrived.
I mean we could probably use a deferred, right, to manage making sure that we take the first, then
We
we
could
like
write it, but invert it. And I could then run.
so basically we would run with both followed by with both inverted, right? We'd have
Or two things in parallel, one with both and the other with both inverted.
yeah, and then there would be a deferred like sitting basically in between the take inside with both, and we would complete the deferred in with both inverted. Like await the deferred, then complete it.
No, that would create a deadlock, artificially a deadlock between the deferred. That's not like the deadlock has to be created by the semaphores
Right.
being taken out of order. So probably an effect delay of 1 second, and this wouldn't deadlock. I was thinking effect.all, so twice this but with both inverted, with both, but I'm not sure this even deadlocks.
So, I mean, like, I think this is a perfect example of like, it's even hard to reason about deadlocks when you're trying to create them. So, like,
It doesn't, of course.
yeah, I mean, we'd have to produce the deadlock artificially, right? So, if we ran, what if we ran, um, what if we delayed the inverted one? No, we'd have to have like
And the point
something.
is, the let me try something else. Maybe so. Takes the first, waits 10 millisecond, take the second. The inverted first takes the second, and then tries to take the first. I'm pretty sure this is gonna deadlock. No.
Are they running concurrently in effect at all? Do you have it set to concurrent mode?
Jesus! So it might have deadlocked.
It might have even deadlocked before without the sleep.
I'm not sure about that, but
I'm not sure about it either, but
no,
no.
that's not the case. But probably this is now that deadlocked. No, no, no. First, second. I want to see what happens.
So the first acquires everything. Well, that's interesting. That's somewhat concerning.
Mm-hmm.
Yeah, let's affect that tap error cause. Good old.
Hmm.
Uh,
So it seems like we have a bug somewhere.
yeah, that's interesting.
Why would this complete?
Why would it
Like,
complete without logging anything?
yeah. Did it even get there?
Mike's favorite
Hmm.
debug log. Neat.
Hmm.
Okay, so we have two fibers. If they deadlock, the program shouldn't ever complete.
Yeah.
This is very suspicious.
Well, actually, it's not, and I think I know what's going on. The point being, if there is no handle and nothing else that should occur, the JavaScript stack is empty. So in this case, we have taken a, a lock. So we've taken the first semaphore, or rather, we've taken the second semaphore. We had a sleep that occurs. Then what's next? I can't continue unless something changes. So the event loop is empty, and the current stack is empty. So the process is terminated. This is why, for example, in effect.never, we have this set interval. Effect.never, in theory, could just be that. I'm creating an async effect, then I never resume. Why I need this fake set interval that does absolutely nothing? So that there is something in the event queue that prevents the JavaScript process to exit.
Right. Well, I guess this is technically demonstrating the deadlock.
Technically, yes. I'm not sure if in run main, not runtime, run main. Let me. This I'm not sure if I've added this background process in the. Yeah, I
Yeah,
did, because this creates a background process
that keeps the handle to the program
that
open.
keeps the. Yes, there's basically a handle registered, uh, but that proved the deadlock. You see, we are in a case where we are
No bug.
deadlocking the thing.
There's no bug.
and and now you might say this is artificial. Yes, it is. But this is far from artificial. Because putting a sleep, okay, it's something that you are manually doing. In this case, I'm yielding, and fibers can yield at any point in time, in effect. So between those two operations, the fiber runtime might decide that it had enough with this specific effect. It yields, lets something else run, and then continue. This should still deadlock. If this deadlocks, I'm absolutely amazed. You
If it
see?
doesn't deadlock.
This is this is
Yeah,
not
this
completing.
this is expected behavior.
This is expected behavior, but this is not completing. In an STM transaction, there's no way that you can yield when the transaction occurs. There's no way that this situation ever occurs. So It wasn't that easy to create the deadlock, of course. Like that's expected. Race conditions are not intuitive, but here, if I invert them, and I do this second part, clean up this so it might maybe fits in the screen. There is absolutely no way that we can make this program deadlock. We cannot add a yield here. And again, those things can happen against your will. So, like, now we've manually created a deadlock situation. With STM, there's no way of creating one, not even if we wanted to, which means it can't happen in a real world use case where it's much more complex than just two operations run concurrently. So I guess that can be it for semaphores. We're just gonna show now the example with queues to see another use case, another potential use case.
Yeah, this I thought was
And
cool. I was looking at your PR on this, and I thought it was kind of a very cool use case of STM.
now in the PR, it's slightly more contrived. I'll show it. I'll show it later. But even a very normal, normal looking thing. Let's get rid of this and let's start empty. Q1 equal yield q dot unbounded, and let's say we want a queue of numbers, and then we want a queue of string q2. Then let's say I have a process that sleeps a random time.
Is it, there's a question in the chat. Is it correct that STM has more strong properties than effect, or is it completely different fields? I'm not entirely sure I understand the question. Could you elaborate on what you mean by strong properties? And then perhaps we could answer that question a little bit better.
So here we have one fiber that fills up Q1. Now one fiber that fills up Q2. Actually, let's make them both of string. So at least we have a differentiator. So Q1, Q2. There's no Q3 and Q4 because the company failed. And this was an accounting joke because counting period works in quarters. We refer to Q1, Q2, Q3, Q4. Not an easy to understand joke. Apologies. Okay, we are filling up the two queues at a random time, and now the task would be take from either of those queues and print the string.
And what's the condition for taking from either of them? Like if there's an element to actually take, or you just take randomly from either?
Just take from either.
Okay.
Like, how would you even go there? How would you even do that?
Take from either of those queues. Well, the second we take from one, if the queue is empty, we're just gonna
Wait.
like wait. We're just gonna end up like like suspending until there's an actual element to take. So we can't.
Okay.
Uh, right?
So that
I mean,
doesn't work. We can check if a queue is empty or not.
right?
We have a function which says queue size or is empty. So we could, in theory, say if first is not empty, take. If second is not empty, take.
Okay.
But we would need to build a loop to do that, to take the elements progressively. Let's do it. While true, if yield q dot is empty, q1, so we want to say if it's not empty, then we want to take q1, then if the second is not empty, we do the same. But if they're both empty, what happens?
Yeah, we just loop forever, like never stop.
This could be one solution. We just on and pull, which is not very efficient. You can see that it probably works. But we have an infinite loop. We have something that keeps looping. If we do console.log here,
Yeah, we're just wasting CPU cycles.
and if the elements are faster than 10 millis, well, actually it would work, but we have to, like, here we could place a yield now, we're wasting CPU cycles. And it's again not efficient at all. Now let's do a very small change. Instead of queue, I'm gonna have a transactional queue. As you see, I'm mostly changing the letters from the rest of the program. I remove this crap. I convert this to an STM gen. Yielding. You see, I'm basically doing an exercise of replacing on stake from either queue, and I can then have my program which says take from either queue, fact.flatmap element.
And maybe for like explicitiveness, we could just wrap the take either from queue and an stm.commit. Even
We
though
could.
that's so the second that you pipe an STM into an effect, it does a commit behind the scenes the same way that you would, the same exact way that that yielding an STM does an STM commit behind the scenes and whatnot.
Yeah, this is basically, it's basically the same. Uh, and to be frank, that's a larger discussion. We are not quite sure about subtyping for the future. Uh, with Effect 3.0, we went all in on this subtyping thing. So most of the data types that you find in Effect, like options, references, and so on and so forth, they are subtypes of Effect, but they do create some troubles with auto flattening because sometimes you get unexpected results. I think for 4.0, we will allow you to yield those types if you want to, but they wouldn't be subtypes of Effect. So in this case, you would have to explicitly say stm.commit, which is still in discussion, but I think can make things a little bit more explicit and a little bit less surprising. But
Yeah.
that's beyond the point of STM. It's really a general thing. Now I've left the console log here for the purposes um, of demonstration. Prints a lot less here. Now it still prints it a few times. Actually, I'd be curious to know why it's printing both.
I guess it is gonna
Because
attempt.
we're taking an element too.
Yeah, because it's filling up the queues asynchronously, right? So it's going to do the check and then retry if either queue is empty or if both queues are empty, right? So it's going to have to check at least a few times in between when it can actually take an element, right?
There's probably some, again, it's not guaranteed to run once, but point being, it runs way less times than it was running before. And especially if no changes happen over the queues, it's never gonna loop, which means we're not running. Um, well, this is atomic, so we are not. There's nothing artificial here. This continues only if one of the two queues are um, are not empty. And the other important element is, given all of this is atomic, if by any chance this take gets interrupted, none of the queues lose the elements, which is the case with effect dot with the effect queues. If you have an open taker that you interrupt and there is a race condition, you might lose an element in the queue. Now again, the queues for the effect queues are meant to never be interrupted, so they are like global things. So you're not supposed to interrupt a take, uh, but that is a valid use case sometimes. When I was developing a very early version of effect actor that now is becoming effect cluster, I had a very similar API to the one we have now, and my mailbox was simply a queue, and I had an issue because interrupting an actor would raise condition on the mailbox, potentially making the actor lose a message. Which, to be honest, we might even have this now. Uh, I'd need to check the internal details of how mailbox is implemented. But worst case, we can use a TQ, and there's no risk of that ever occurring. So this is STM. I will now quickly show the PR that we were working on. So the PR is this one. It's add T subscription ref that a user wanted. So it's a transactional subscription ref. And this has been going on for a long time, partially due to my fault of having not reviewed this deeply enough to begin with. And to summarize a little bit, a subscription ref, it's a reference where you can also observe the changes. And the default subscription ref uses a stream for the changes. So when you subscribe, you get back a stream of changes that contains the current value and potentially also the following changes to that value. In this case, we want the same but transactional. And initially, this user was implementing the changes as a stream, but a stream is not transactional. And Tim rightly pointed out that I think this should be an STM of a TQ, more precisely an STM of a TDQ, so that there is transactionality. So you could use that subscription inside an STM transaction. And this took a while, and the user was like, I'm having a little bit of troubles because I would need a way of merging TQs. And he sort of made the point in this way, where basically he's creating an unbounded queue, then it's getting a reference, getting the current value, pushing the current value on the queue. So this is the first value, then subscribing to the pub sub of changes. But then how does it work? They can't create a stream out of it. STM cannot fork a process. So it's like, how do I make a TQ that has the first element of the current value and the rest of the elements, the change stream? Basically, the rest of the elements are the individual changes. And I was like, changes doesn't contain the current value usually. And I was pointed to the comment that actually it does. So I was dead wrong. I was like, then we just probably need to implement the TDQ interface with a custom implementation. And yesterday I had a little bit of trying, and with this commit, I actually made it work. So basically, I created a custom TDQ merge that implements the TDQ interface, which can be constructed with two queues, first one and a second one. And then I've basically done exactly what we've done now. So I've went through implementing every single method. So let's, if we see pick option, how it is implemented. Well, it's an STM generator where I first pick the first queue. If there is an element, I return it. Then I do the same on the second queue, and I keep going. The take is exactly the same code that we've done now. We check if the first is not empty, we take from the first. If the second is not empty, we take from the second. And I kept going, implementing all of the methods on the TQ. And this was fairly surprising to me because, again, this is absolutely impossible to do with a normal queue. And I thought this was really nice, and this kind of shows again why STM is actually very powerful, especially for those contrived use cases. So we've roughly went through everything that is required to understand this example today in code with live examples. But this is actually how you then manipulate those transactional structures in real life, even to create, again, custom data types that can act transactionally. So now the final interface for this PR ended up. Let's just see it in action. The subscription ref. Let's have a look at the interface. It's slightly simpler than the tests. We have a stream of changes that is an STM of a TDQ, and we have a lot of functions that are very similar to the ones we have in the normal subscription ref. For example, we have changes scoped, changes stream, the normal changes that gives you back the STM of a DQ. And if I go on and see how this changes stream is implemented, I can quickly show that. It's basically using the changes and then creating a stream from a TQ with a shutdown, which is also a function that we should expose, because I believe at the moment we are not exposing the way of creating a stream from a TQ. But once the main job was done of creating the joint reference, then everything else was like almost a line of code. Changes scope does the same thing. It acquires that, and then on cleanup, it shuts down the TQ. Shutting down the TQ removes the subscriber. And yeah, uh, that was that was it. It was slightly long and contrived, but I hope that at least Maxwell has an understanding now of transactional operations with effect.
Yeah,
If
no,
you have
this was
any
great.
question, I'm happy to.
This was very good. I feel like I've got a much better handle on the how to actually use STM now. If anybody in the chat has questions, feel free to post them. Otherwise, you can ask in Discord. But I feel like there is definitely a lot of use case for STM within cluster, given how much synchronization we actually have to do. Um, so yeah, I don't know. I think it's gonna like require a little bit of thinking, but I can definitely already think of some possible use cases for STM. Just gotta look and see if it actually fits the use case or not.
Good, which I think is probably gonna be one of the topics of the next stream on effect cluster.
For sure. So cool. Well, thank you
Good.
very much, Mike, for taking the time. I think this was very useful, even for nobody else. That it was useful for me. So
Yeah, apologies again. This was meant to be an explanation to Maxwell, so I wasn't really starting from zero. But hopefully, it's helpful for somebody else too.
cool.
Maybe at a reference point, when you get to the point of like, maybe I need STM, you get here and it's like watch the recording, and then it'll make sense at a later point in time.
Yep.
Good.
Well,
Then
thank you,
thank you very
everybody.
much, and thank you everybody for sticking with us for an hour and a half.
Cheers, everyone.
Cheers, folks.